Hello everyone. This is the mechanics of material. Mhm. And this part we are going to another section. Okay, it's called stress and strain. Okay, stress and strain. We'll introduce a new concept called stress and strain. And in the previous section, we have introduced to show you how to calculate the internal force of material. Internal force of material. Internal force of material. When we apply external loading on the material inside the material itself, we will create some internal force to make the whole system static. Okay, and we previously we said the internal force there will be when you apply external load to a material, that would the material will generate the shear force, the normal force, and sometimes also created a bending moment. Okay, and here we want to introduce the new terminology called stress. Okay, stress. Okay, and at the beginning, I have to address that the stress is not equal to force because sometimes people finally will scramble with these two terms. Okay, here we will introduce the terminology called stress, but it's not equal to the force. Okay, when you check the unit, the unit of force is Newton, okay, and the unit of stress is Newton per meter square, okay, and we will later talk about the definition of stress, okay, and you will know that its unit is Newton per meter square, and it's in SI system, okay, we call it Newton divided by m square is also called PA, okay, Pascal. Pascal. Okay, okay. So let's start because in previously we say the internal force in the material we have two kinds of internal force. The one is normal force, the other is called shear force. Okay. Okay, for the normal force means the force is acting normal to a surface, a surface. Okay, that's called normal force. Okay, and here's a normal force. Okay, normal force. We will have also have a terminology called normal stress. Okay, normal stress. Okay, and shear force. Shear force. We also have a terminology called shear stress. Okay, shear stress. And stress. What is stress? Stress is the intensity. Okay, it's a force divided by area. Force divided by area. And in this class, normal stress, we use the sigma to represent the normal stress. Okay, and okay, so then the right hand side is a tiny element in the material. For example, if there is a beam or bar here, okay, and they cut a small element here, and it become like this. Okay, okay, and you see, okay, sigma is a normal stress. There's a normal stress z direction, normal stress x direction, normal stress at y direction. And normal stress is the normal force. Normal stress is normal force divided by the area. Okay, area. And be careful, and also be careful the normal force and the direction of normal force and the direction of area must be the same. Okay, they must be the same. That's called a normal force. Okay, for example, the z direction stress at z direction, it's a force at z direction be divided by area divided by area along at the z az. Okay, az it's hard to say how to describe az. Az is here for okay. Az is here. Here is az. Here is az. Here is az. Okay. and here is ax, and this surface is ay. Okay, ax, ay, az. That means the surface vector or normal vector of the surface is pointing to z direction. Okay, and x means the surface normal. Is that terminology called normal? Yeah, normal vector of surface is point to x direction. That's called x. And ay means the normal vector of this surface is point to y direction. Okay, so I think I should make this clear statement. Okay, ax means the normal vector. OK，中文口法向量。The normal vector of the surface is pointing to the x direction. That's called ax. And the normal vector point to y is called ay, and normal vector point to z that's called az. Okay, so when you're trying to calculate the normal stress, be careful the direction of stress, the direction of force and direction of the area must be the same. That's called normal stress. That's normal stress. Direction of force, direction of area must be the same. That's called normal stress. Okay. Okay, so that's the normal stress. Okay, and there is all and so since we have normal stress, there is another terminology called shear stress. Shear stress is also an intensity. Okay, but what a difference between the shear stress and shear stress and normal stress is the direction. Okay, direction. What does that mean? Okay, let's see the other slide. Okay, let's see the other slide. Okay, so okay, let me erase this. Okay, let me erase here. Okay. Let me erase this. Okay, this part. Okay, we still use this the element. Okay, small element of material. Okay. Okay. Okay, just like the normal stress, shear stress is also an intensity. It's also a force divided by area. Force divided by area. But you see the difference is the for direction of force is not the same as the direction of the surface. Okay, different, right? In normal stress, the direction of force and the direction of surface is the same. Okay, but right now the direction of in shear stress, the direction of force and direction of area is not the same. Okay, let's see. Okay, and in this course, okay, we use the tau. We use the tau to represent the shear stress and sigma to represent the normal stress. Okay, let us see. In the normal stress, we only have one indices. We only have one indices. Okay, what's the indices mean? Okay, in previous slide, normal stress only have sigma x, sigma y, sigma z. That's only one. It only has one index. Okay, only one index. Okay, but now in shear stress, we have two indices. Okay, indices. Okay, or two label. Okay, maybe use label is much easier to understand. Okay, we only have one label. Okay, we only have one label. Okay, but in shear stress we have two label. Okay, two label. Okay, and then you have to know why there's a two label. Okay, so for example, if I write a sigma I, tau ij. Okay, what does I mean? What does j mean? Okay, the j it means the direction of force. Okay, direction of the force. Okay. And what is it? I mean, is the surface direction, surface direction. Okay. Okay, here we see, okay, here, tau zx, that means the force is in x direction and divided by area, the surface direction, divided by z, so that means az. Az means the normal vector is pointing to z direction. So, sigma zx is here, sigma zx is here, okay? Okay, you see its force is point to x direction. Here, force is point to x direction. Here is x. Okay, here's x. Force is point to x direction, but its surface is here. The surface here is the surface, the normal vector of the surface is point to z direction, so it's az. So okay, so this call is called shear. This is it's called tau zx, tau zx. And we can also see that in shear stress, the force is tangent to the surface. Okay, tangent to the surface. Okay, it's different from normal stress. In normal stress, the force is normal to the surface. Okay, but in shear stress, the force is acting tangent to the surface. Okay, that's called shear stress. It's called shear stress. So the difference between the normal stress and shear stress is just it's the direction, and you need to I think you need to get familiar with that, okay, that concept, because I don't think previously you I think I'm not sure in your first year physics or other course talk about shear stress or not, okay, but yeah, you should you should convince yourself this concept, okay. A normal force is simple. Normal stress is simple. The force is normal to the surface. Okay, and shear stress, the force is acting tangent to the surface, and in yeah, and in shear stress we have two labels. Okay, in shear stress we have two labels. One is for direction of force, the other is surface direction. Okay, so that's a little more complicated. Okay, normal stress, we only have one label. Okay, X, Y, Z only. Okay, okay. So, but actually, in very detail, actually, normal stress, we can also use the two label for normal stress. But I don't want to. I won't talk about this in very detail because I don't want to. I don't want to. I don't want to. Make this topic too hard. Okay. Okay, so okay, and let's see. Okay, and let me erase the other example. Let's see this example. Okay, let me erase this. Okay, so here is a tau zy. Okay, the second label is directional force. So what that means, the force is acting along the y direction and it's on the az surface. Okay, force in y direction and acting on az surface. So force is a y direction. Okay, which one? Force is on az. So let's look at here. Okay, here's a tau zy. Okay, yeah, you see the force is along the y direction. Y is here. Okay, force along y direction is acting on az surface, so it's called tau z y. Okay, again, you can apply this same concept to the other four shear stress and check the label is really what it means. Check the label, the meaning of this label. Okay, convince yourself. Okay. Okay, so that's the shear stress and shear force. Okay, shear stress. Oh, sorry, normal stress and shear stress. It's just like the intensity. Okay, it's just a force divided by area. Okay, that's called intensity. Okay, force divided by area. That's called intensity. Okay, so since it's force divided by area, so it's the unit of stress is Newton divided by meter square. In SI unit, we love the NKS system, right? Newton, meter, kilogram, and second. Okay, and Newton divided by meter square is called Pascal. Okay, don't forget about the Pascal. Okay, so that's the introduction of the shear, normal stress, and shear stress. Okay, okay. Normal stress and shear stress. Okay, what else do we have on this slide? Let's see. Let's see. What else do we have on this slide? Yeah, that's not really doesn't have really new. Okay, just a summary. Okay, what is here? Okay, general status. This stress is incorrect. Yeah, I think there's nothing nothing very new from this slide. Okay, just also the summary. Okay, and okay, let's see. Okay, and okay, in this topic, yeah, I think I need to address some previous slide. State stress. Yeah. Oh, did I miss him some? Okay. Yeah, never mind. Okay. Okay, so and this slide I just want to talk about. Okay, in this course in mechanics of material, when we do the calculation, we all assume the material is homogeneous and isotropic. Mhm, homogeneous and isotropic. Okay, and this is we have make this assumption to let us do the calculation. Okay, you have to assume that material is homogeneous and isotropic. And what does that mean? That does not that mean the physical property or mechanical property of the material is the same in every part of this material. For example, for this bar, okay, maybe this bigger. For this bar, okay, and later we will talk about very important mechanical property called elastic modulus. Okay, elastic modulus. Okay, modulus. It use E to we use E to represent the elastic modulus. Okay, and we assume the material, or when we assume the material we have, the elastic modulus is the same in everywhere, in every part of this material. For example, just assume we assume the material, the elastic the modulus is E, okay? And that means at this part, the modulus is also E. In this part is also E. This part is also E. This part is also E. Every part of this material, the elastic modulus is all the same. It's all the same. That means that just means homogeneous and isotropic. Yeah, yeah, it's the same physical property and mechanical property throughout its volume, and it has the same property in all directions. So that means your mechanical property, like elastic modulus, is the same in every part of this material. That's our assumption for this course. Okay, but actually, in reality, it's very difficult to make a material very isotropic. I think it's very difficult to make the material very isotropic or very homogeneous. It could be very close to homogeneous isotropic, but yeah, because it's very difficult to make sure your material has no perfect and no defect, no defect, and every physical property in every part of material is all the same. It's very difficult to make a guarantee to make to guarantee this happen. It always has some impurity in material. You always have impurity in material. Always have some defect in material. So, the mechanical property or the physical properties, yeah, it's use a common sense. It's very difficult to make sure that the physical and mechanical property in the material, every part of the material are all the same because impurity and defect. Okay. Okay, but now all we can do is minimize our defect or minimize our impurity to make the material like homogeneous or like isotropic. Okay, but in our calculation in this course, we just assume a material, the, the material property is homogeneous and isotropic. That's easy for calculation. Okay, but that's a little different from real world. Okay. Okay, and yeah, and later it say if we calculate the axial loading when we apply a load this bar through the centroid, its cross sectional area, the bar will we also assume it deform uniformly throughout the central region of its length. Okay, it will deform uniformly in each part of this material. Okay, that's the assumption. Okay. Okay, that's assumption. Also isotropic and homogeneous, you will have this situation happen. Okay, if you apply external loading like axial loading, every part of it is the material experience the same loading and deform uniformly throughout the central region of its lens. Okay. Yeah, yeah, yeah. That's well. Yeah, but actually, it's very ideal. It's very ideal. In real situation, maybe there's some difference. Okay. Okay. So let's is your assumption we made in this course. What's next? Okay, so the more normal stress, yeah, we just say the normal what is a normal stress. Normal stress is the normal force divided by area. So when I apply external load on the bar, we have some tension. I apply tension on the bar. Yeah, you will have the normal stress. You will create normal stress in the material. Okay, and normal stress is you apply the normal force divided by area, and I also can compress the bar. Okay, okay, it also will create a stress in the material. Okay, and just different direction. Okay, different direction. Okay, just different direction. Extension and compression, they are in different direction. Okay, I think it's very easy to you can imagine when you apply the external load on the bar, you will create a normal stress create normal stress in the bar. Okay, and okay, so in the next we will have the three very simple example for the normal stress calculation. Okay, and normal stress calculation in this video, I'm just show you the simplest one, 7.6. And in the later two video, I will show you 7.7 and this example from the textbook. So this video, I just start with the example 7.6 because it's really easy. Okay, it just want you apply the definition of the normal stress. Okay, and what's a normal stress? Okay, it's the normal force divided by area. Okay, and be careful. In normal stress calculation, your force and your surface must be on the same direction. Okay, and here, this is example is here is a lamp. Okay, it's 80 kilogram lamp is supported by two rods A, B, and BC. Okay, and it give you the diameter of the A, B, and BC. Okay, okay. So there's a terminology here. If you don't understand what's the diameter in 中文 is called 直径. Okay, diameter is 直径. Okay, diameter is 直径. Okay, and radius is 半径. Okay, be careful. Okay, because sometimes, yeah, in some problems, sometimes the problem give you a diameter, some problem give you the diameter, some problem give you radius, and you must be very careful. Okay, because sometimes you will scramble these two, and all your calculation will all wrong. Okay, yeah, you have to be very careful, because it's really happens. Your calculation scheme, your calculation process are all correct, but you just misuse the diameter and radius, and so that's why your final result is wrong. Okay, that happens a lot. So be very careful. It's diameter or radius. Okay, because this will influence your calculation area. Yeah, because don't forget the stress is the normal force. No, a normal stress is the normal force divided by area. Okay, so the radius and diameter is let you to calculate the area. Okay, so be very careful. Okay, okay. So what's this problem want to calculate? Determine the average normal stress. Okay, okay, and normal stress. Okay, sometimes in some problem it will call the stress is called average normal stress. Okay, actually it just I don't think it's almost the same with this. normal stress, because the normal force is divided by areas. Okay, that's why it's called average. Okay, because it divided by total area. So sometimes some problems say this, some book will say this is called average normal stress because it's divided by the total area. So that means average. Okay. Okay, so let's see. Okay, so what's the problem? Hell, okay, so let's finish the problem. Okay, so you want to calculate the sigma BA and sigma BC. Okay. Okay, so okay, with you the definition of the normal stress, we need to know FBA. Okay, also we need to know FBC, and FBA you must divide it by ABA. Let's say, okay, okay, ABA, and this is ABC. Okay, you need the force and area. Okay. Okay, so let's see. So first of all, how to calculate this force? Okay, because this length, suppose this is a free body diagram. Okay, don't forget. Okay, this is a free body diagram of this problem. Okay, so the length is 80 kilogram, but be careful. This is a mass. Okay, this is a mass. Okay, and now we want to do the force balance, static force balance. We have to convert the mass to force. So this problem you have to times the 9.81. Okay, it's kilogram times the acceleration is equal to its weight. Okay, weight is a force. Okay, so that's why he in AT has to time 9.81 to become a force. Okay, and they give you this angle information. Here is 60 degree, and here it give you the ratio of this right triangle. Let's give you the angle information. So okay, so what's called what can we calculate FBA and FBC? I think it's very simple because this is looks like a 2D problem. Okay, 2D problem and do a force balance. How easy is that? Okay, and let's see. Okay, sigma everything is static. Sigma Fx is equal to 0 because everything is static. Okay, in this course everything is static, so sigma F equal to 0. Okay, let's consider the force x direction. So here we have FBA and cosine 60 degree. FBA cosine 60 degree, but it's pointing to the left. So we have negative sign. And here we plus FBC and cosine. Okay, of course theta. I agree that cosine theta, but cosine theta is 4/5. And anything else in x direction? Nope. Okay, 0. Okay, and then fx divided by y equals sigma. Y component is 0. Okay, so FBA, okay, is times sine 60 degree. It's point up, so it's positive. And FBC times 3/5. Okay, point up. It's okay. Okay. And anything else in y direction? Yeah, we have here 784.8 Newton point down. So it's negative 784.8 point down is equal to 0. Okay. So we have two equation, right? Yeah, we have two equation and we have two unknown. I think we can solve the problem. Okay, so I just write the FAB and FBC for you. So don't forget calculate by yourself. Okay. And don't forget calculate by yourself. And here let us see. Okay, FAB. I think FAB we will have the answer. Like FAB is um 632.4 Newton. Okay, FBC is 395.2 Newton. Okay, okay. I think we have the we have the force AB and force AB and force BC. Force BA. Sorry, force BA. Okay, so okay here. Okay, 3.4. Okay, It's 395.2. Okay, the other thing is calculate the area of BA and area of BC. Okay, AB and BC is give you a diameter. Okay, AB is 4 millimeter diameter. BC is 8 millimeter diameter. Okay, and so, but just one thing I want to address that because this is a very thin bar. Okay, this is very thin circular bar, very thin circular bar like this. Okay, very thin circular bar like this. So the force is always normal to this is a bar. Okay, this is a bar. Okay, this is a bar. Okay, that means the applied force is always apply this to attention. Yeah, tension always normal to surface. Okay, normal to surface. Okay, because in the surface, in the normal stress calculation, I just mentioned that you need to make sure your surface direction and your force direction is the same. Okay, okay. So that means your force direction is always normal to your surface direction. Yeah, normal to your surface. Okay, okay, the force is always normal to the surface. Okay, the force is always normal to the surface. Yeah, the force is always normal to the surface. I'll make sure that. Okay. Yeah, I think I misused some terminology. Okay. Okay, never mind. Okay, the force always normal to the surface. Okay. Okay, so how to calculate the surface area of this bar, circular bar? So if give you a diameter, so the area is equal to pi over 4 d square. Okay, so here is pi over 4, here is pi over 4, and AB is 10 millimeter. Okay, diameter 10 millimeter. So 10 millimeter, don't forget, 10 millimeter is 10 times 10 to the power minus 3 square. Okay, 8 millimeter is 8 times 8 to the power minus 3 square. Okay, don't forget this prefix, this small m means the 10 to the power minus 3. Okay, millimeter, small m means 10 to the power minus 3. Okay, and here, and for this calculation, it's better to use the megapascal. This is not, this should be capital. That should be megapascal, using the megapascal. Okay, because after do the calculation, you will find this is 10 to the, because the square, it will become 10 to the power minus 6, and it's on it's at denominator, so it will become 10 to the power 6. Okay, so it's better to use the mega. Okay, use the mega, use this prefix to represent your answer. Okay, or you have to write lots of zero, right? Okay, so you can check yourself to see to see, you can check this by yourself. I think the answer is correct. The answer is correct. Okay, I didn't write the answer. Let me check. For AB, let me see. For AB, let me check. Okay, let me check. 10 times 10 to the power 3 square times 4 divided by 4. And yeah, it's equals normal stress BA is 8.056. Okay. Okay, normal stress BA is 8.056. Yeah, that's correct. And the other is 8 times 10 to the power minus 3 square 0.14 divided by 4 inverse 395.2 divided by 10 to the power 6. So the normal stress BC is 7.866. Yeah, megapascal. Yeah, the answer is correct. Okay, so this is a very simple example to just let you want to know to use the definition of stress. Okay, Yeah, this should be megapascal. I should modify this. Okay, so I will update this line. Okay, so I just start the video here. Okay, see you in the next video. Okay, bye bye. Yes, capital. Okay, I'll update this line. Okay, see you. Bye bye. Hmm. Video long, too long.